Welcome to the Physics Odyssey channel, where we answer really hard questions using the laws of math, physics, and some common sense. Here's a recent picture of some of my colleagues. I actually was just a little bit late to this picture, so I wasn't able to get in on this very important picture. If you like the content, please subscribe. It only takes about 10 seconds of impulse to do this. And you'll see some up-and-coming content, including more busting MythBusters, virtual myth busting, physics of stupid stunts. I'll release this soon. Amusement park physics using simulators. It's a lot of fun. Astrodynamics using simulators. Some advanced physics using Blender animation. Just got a new dog, so I've come up with some interesting videos with the dog. It looks like the dog actually understands a little bit of physics, so I thought that'd be kind of fun to do a dog physics video. I published a video on Rattleback, the physics and mathematics of the Rattleback. So I'm going to release another Rattleback video and my favorite Feynman from the Feynman lectures. So this is a review of MythBusters Crash Force episode, Season 8, Episode 6. The myth: a car traveling at 50 miles per hour colliding head-on with another car at 50 miles an hour is equivalent to a car colliding with a wall at 100 miles per hour. A lot of great physics here. Many in the physics community said that Jamie had it wrong. Okay, we'll see about that herein. Great experiments by MythBusters led me to make a really interesting insight relating kinetic energy of a car to the amount of damage done to the car. Other physics topics that I'll get into: spring energy and force, kinetic energy, momentum, conservation energy, momentum. And from what I've learned about an appropriate equation that relates kinetic energy to damage to a car, I've come up with a design for the safest cars on the planet. To my fellow teachers, email me for a discussion set for students related to this video. Okay, let's start with Jamie's statement at 1:34 into the episode.
What's up?
What's up is that the fans are in control. It is effectively Mythssion control.
So how does that work?
Cast your mind back to Compact. Remember we smashed two semis into each other at 50 miles per hour, which you said on camera was equivalent to one of them hitting a wall at 100 miles an hour. And the fans went nuts. They are revolting. They rose up and they said, no, two cars hitting each other at 50 miles an hour is not equivalent to one hitting a wall at 100 miles an hour. It's equivalent to one hitting a wall at 50 miles an hour. They say that you were wrong.
Let's test it.
That's what I thought.
It was the episode that had it all. Crashes.
Wow.
Smashes. And according to fans, a subtle physics faux pas.
Both trucks were traveling at about 50 miles an hour when the impact occurred. Now that's equivalent to a single impact going into a solid wall at 100 miles an hour.
Stop right there. This innocent remark.
Now that's equivalent to a single impact going into a solid wall at 100 miles an hour.
Sparked a fan frenzy. They reckon that because of Newton's third law, every action has an equal and opposite reaction. The two cars crashing at 50 miles per hour is the same as one car crashing into a wall at just 50 miles per hour and not 100. But can this counterintuitive argument really be right?
Well, if fans are in control, how do they want us to do it?
Obviously they want us to smash some full-size cars in.
So Jamie's statement: both cars were traveling at 50 miles per hour when the impact occurred. That is equivalent to one truck hitting a solid wall at 100 miles per hour. This is what I'm going to analyze. Jamie didn't make it clear by what he meant by equivalent. Was he referring to impulse, energy, damage? Those are the three I can think of. I'm going to analyze both of these collisions with respect to impulse, energy, and damage. Also, he didn't refer to whether he's referring to the two-car system as the damage to one car or the damage to both cars, or the energy of one car or the energy of both cars, or the impulse required to bring a car to stop versus two. I'm going to look at both. I'm going to call it System 1, two cars colliding at 50 miles per hour, and analyze the impulse energy damage versus one car colliding with the wall at 100 miles per hour. Looking at impulse energy damage, then I'm just going to look at one car related to these three variables. Jamie is correct. If he was referring to the required impulse to bring two cars to a stop, traveling at 50 miles per hour, versus the required impulse to bring one car to a stop, traveling at 100 miles per hour, they're the same. Impulse is defined as force times the time over which the force is applied, and that's equal to the change in momentum of an object. Mass times velocity is defined as momentum. In a car collision, the final momentum is zero because the final velocity is zero. It has hit the wall or the other car. The initial momentum is the mass of the car times the velocity of the car the instant before impact. One 1,000 kilogram car traveling at 100 miles per hour, I'm using meters per second here, 100 miles per hour is 44.7 meters per second. The magnitude of impulse would be mass times velocity, 44,700 newton seconds. Two cars. Let's look at one car traveling at 50 miles per hour, which is 22.35. One car would be that, 1,000 times 22.35, which would be 222,350. But two cars, there are two cars colliding. So what's the impulse required to bring both cars to a stop? 44,700 newton seconds. They're the same. But if Jamie was referring to the damage done in energy, let's look first, before getting into that, the second collision, which is a 100 mile per hour car hitting the wall, and then we'll come back and talk about the physics.
Now, the 50 mile per hour impact clocked an impressive 58 Gs. But will doubling the speed double the damage to this car?
Good. I gotta say that after watching that 50 mile an hour crash into the wall, I have a really hard time imagining that the 100 mile per hour crash is gonna compress the car that much more. I don't know.
So are you ready for some more wanton destruction?
I am! Let's go twice as fast.
All right.
Wanton destruction it is, as the MythBusters retire to a safe distance and the countdown begins.
You ready to make this happen?
I can't wait. I haven't seen a 100 mile an hour crash before.
No. All right, commence with the 100 mile per hour crash.
On Adam's command, the engines whir into life, straining to get the car up to exactly 100 miles per hour. It hurtles down the track.
It's going flat out.
The cable uncouples, and the car plows into its final destination. The guys are understandably speechless. That impact crushed the lemon car with such force, it should be in a glass with ice and a cocktail umbrella.
It's in a very different state than it was at 50 miles per hour.
Yeah, it's a little shorter.
I mean, we got a clear difference between the two crashes.
Uh-huh.
I can't wait to see what the data set says about the G-load.
If the data's still intact.
If anything's still intact.
Well, thanks to its position in the trunk, the black box survived.
But did we successfully retrieve anything?
We've got good data.
Really?
Yeah, we've got a peak on the left side of 140 and a peak on the right side of 230. And we normally just average those to get a result there.
So the midpoint's somewhere around 185?
185.
That's nice. That's significantly more than, what was the last one? 58?
58.
Data.
3 times the G's of the 50 mile per hour test is certainly significant. But that's not the only data set they're collecting.
Before it was 15 feet. Now it's 8 feet.
So not only did the G-load triple, the crash compacted almost half of the car. And remember, these two cars were identical.
This may just seem like some gratuitous violence, but there's actually some really interesting science going on when you compare these two impacts. You would think that doubling the speed would give you twice the severity of the impact, but the physics says you're actually looking at more like 4 times the severity of the impact. Our sensors are showing 3 times the G's, and our wreckage is showing about twice the damage. So what's going on here? Well, just like this can, the more I crush it, the more it resists crushing. There's some complex physics going on here, but you don't have to be a rocket scientist to understand it. The cars speak for themselves.
They certainly do. And after 2 spectacular crashes, they have their benchmarks for car carnage.
Well, we've got our data points.
And they are lovely. I guess it's time to move on to the main event.
Yep.
Okay, now I want to talk about the energy required to bring a car to a stop. I'm going to use something called the work kinetic energy theorem. Work is equal to the change in kinetic energy. What is kinetic energy? It's 1/2 times the mass of the car, in this case, times its velocity squared. So the work required to bring a car to a stop means the final kinetic energy is 0, it's just going to be equal to the initial kinetic energy of the car. I thought I'd get off on this tangent a bit. What if the car were a perfect rubber ball or a perfect spring that when it hit the wall, the spring absorbed all the energy? If that were the case, then after it hit the wall, it would spring back at the initial velocity. These equations come from the assumption of conservation of momentum and conservation of energy. And what this equation says, for a small mass, and I'm calling that the car, colliding with a really large mass, I'm calling that the wall, the final velocity of the car would be the same as the initial velocity of the car, just in the opposite direction. This right here becomes -1, approximately -1, when m2 is much larger than m1. The velocity of this, the wall, or a really large object, for m2 much larger than m1, is approximately 0. But the car isn't a perfect spring. As it is compressed, it stores none of that energy. All the kinetic energy of the car goes into compressing and damaging the car. So energy lost in bringing the cars to a stop. First, 1,000 kilogram cars, each traveling at 50 miles per hour, again 22.35 meters per second. That's a fairly simple equation. 1/2 times the mass times velocity squared. 2 cars, about 500,000 joules. 1 car traveling at 50 miles per hour would just be half of this, right? About 250,000 joules. And 1 car traveling at 100 miles per hour would be about 1,000,000 joules. 1/2 times its mass times its velocity squared. So, to conclude, it takes 4 times the energy to bring a car to a stop if the speed is doubled, and 2 times more energy to bring 1 car traveling at 100 miles per hour versus 2 cars traveling at 50 miles per hour. So if Jamie's word equivalent was energy, then he was wrong. It takes 2 times more energy to bring 100 mile per hour car to a stop versus 2 50 mile per hour cars. What about damage factors? 4 times the energy, 4 times the damage? Okay, here's my hypothesis. The crumpled zone of a car is like a one-way spring. The greater the compression, the greater the force required to achieve additional compression. And you saw that in the video I showed you, where Jamie says to crush a can, the more it's compressed, the more force is required to compress it more. And he's exactly right. And when I heard that, I decided to test the force law. F is equal to a constant times the compression amount. Here's a spring, right? The mathematical equation which describes the force of the spring is this, where K is a spring constant. The larger K is, the more stiff the spring is. Okay, that's more stiff than this spring. And what this says is that the further you compress it, the harder it is to compress it more. So how much energy does it take to compress it some amount x? Well, I can use a mathematical operation called an integral to integrate this function from 0 to the amount of compression, x, some arbitrary x. And what I get is 1/2 kx squared. And what this tells me is, let's just say x is 1/4 of a meter, and if I have the spring constant, which you can get for any spring, I can figure out how much energy it takes to compress it that much. So what I did in this analysis is I said all the energy, the kinetic energy of the car is going to go into compressing the car, a one-way compression. So does this explain the MythBusters result? Does my hypothesis that the force law Kx, resulting in the energy to compress a spring some amount x, which is 1/2 kx squared, explain the compression for a car traveling at speed v with this amount of kinetic energy? What I did was I took these equations, so all the kinetic energy of the car goes into compressing the spring, or in the case of the car, crushing the car some compression amount x. Solve for x, multiply both sides by 2, divide both sides by k, square root both sides. Here's the compression amount given a velocity of the car and a spring constant and its mass. What if I double the velocity? Multiply both sides of the equation by 2, double the compression. That's absolutely consistent with the experiments that the MythBusters did in this episode. Conclude, if you double the velocity, you double the damage. And this is consistent with the MythBusters results. So the damage of two cars colliding at 50 miles per hour was the same when you add them as one car colliding with a wall at 100 miles per hour. If you're looking at just one car traveling at 50 miles per hour, the damage is half of that versus one car traveling at twice the speed, 100 miles per hour. So Jamie was correct on this point. I was curious as to what the spring constant of a collision would be. Since this equation seems to explain the damage, I solved for the spring constant given the known compression from the experiment, which was 2.1 meters. Set this equal to this, plugging in everything I knew, didn't know the spring constant, and I got about 500,000 newtons per meter. I've never seen a spring constant that large. Interesting. I then took that information, now that I have a spring constant, solved for the compression of a 50-mile-an-hour car hitting the wall. And they also did that experiment, in addition to the two 50-mile-an-hour cars hitting each other. And I got almost exactly what they got from the experiment. And I already knew that. I already proved mathematically that if you double the energy, you double the damage. Conclude, this force law is a pretty good model for predicting compression of a car in a crash. Again, based on actual experimental results that MythBusters did. Okay. I said, I highly recommend you watch this episode. I'm not going to show you anything more from the episode other than Jamie's conclusion. But it's remarkable the experiments they did and the data they acquired. And I enjoyed the episode. I enjoyed using the data to prove that, wow, the force law of Kx is a really good model for predicting compression in the car collision. But let's take a look at Jamie's conclusion.
I made a statement that two cars hitting each other at 50 miles an hour was the same as one car hitting a solid wall at 100. That was a mistake, but you know what? I'm okay with it. That's how you learn stuff.
I love smashing stuff for science.
So is Jamie right or wrong? Two scenarios. Two cars collide at 50 miles per hour, system 1, versus one car colliding with a wall at 100 miles per hour, system 2. The magnitude of impulse required to bring the two 50-mile-per-hour cars to a stop is the same as that of one car traveling at twice the speed. Correct. 2. Energy required to bring the two 50-mile-per-hour cars to a stop in system 1 is 1/2 of that required to bring the 100-mile-per-hour car to a stop in system 2. He was wrong on this point. The total damage done in System 1, again, 2 cars colliding at 50 miles per hour, is the same as that done in System 2. 1 car traveling at 100 miles per hour. But again, remember, Jamie said equivalent, and I realized that, what does that mean? So I analyzed what I thought were the most important physical attributes related to a car collision. Total impulse, energy, and damage. If we're calling the system comparing one car at 50 miles per hour hitting another car at 50 miles per hour with a car hitting a wall at 100 miles per hour, just looking at the magnitude of impulse of one car versus the magnitude of impulse on the other car traveling at 100 miles per hour, he'd be wrong on all points. It takes twice the impulse to bring a 100 mile per hour car to a stop versus a car traveling 50 miles per hour. It takes 4 times the energy, and a 100 mile per hour car will incur 2 times the damage as a 50 mile per hour car. Okay, so that wraps up my analysis of this episode. I hope you enjoyed it. I learned a lot doing it actually from the data that they were able to acquire. And I decided that I was going to create another episode based on some of the stuff I learned. Again, that the force law is a very good law for predicting compression in a car collision. And so from that, I've designed a car that will max out at 6 Gs when hitting a wall at 100 miles per hour. Okay, at 6 Gs, most humans are probably going to pass out, but they're probably going to be fine as far as physical injury is concerned. Subscribe and I will email you when that is available. And also I'm going to talk a little bit in that episode about how crumple zones minimize Gs on impact. I've actually modeled a car collision using Excel, second by second. It's pretty interesting. So join me for that. Thanks for watching. Bye-bye.